Hello, my name is Deepam Rana.
And my name is Jon Yuen, and we are the double oscillating engine team for the EGR 305 Section 3 midterm project. The double oscillating engine. For our midterm project, we modeled this double oscillating engine. The engine works by rocking back and forth as the crankshaft moves the piston. This engine was used years ago in steam engines, both stationary and on ships, although currently it is most commonly used in toys and models. Moving on, here's how we designed this engine in CATIA.
So this was my first subassembly. This was the main bearing block subassembly. It was used to hold the crankshaft together along with the flywheel. This part was the only one I personally had an issue with because it consisted of a pin that was not dimensioned or shown anywhere else in the project. To counteract this, I designed a pin to be used similar to what was given in the picture. In the end, it was not used anywhere in the assembly as it was purely there just to hold the main bearing in. This is the main frame subassembly. This subassembly consists of the main frame and the previous subassembly placed right on top. This is used to give leverage to the crankshaft and allow the flywheel to rotate fully. In my opinion, this main frame was my hardest part. This is because it had missing dimensions for fillets and the center bar was poorly dimensioned and didn't really show its location. Besides that, the features used to make it were fairly easy. Moving on, this is my third assembly. Going from my hardest part in the previous slide to probably my easiest. This consists only of the port block pedestal and the port block nipple. The cylinder for the engine is connected to this part, and a socket right in the middle allows it to rock back and forth fully. This was my last subassembly. This subassembly consisted of all my previous ones. It also consists of all the fixed parts in our engine. The only new parts added to this were the compression spring and the pivot spindle and our nameplate. To make this subassembly, I had first fixed my plate and then constrained everything to that. Noticing that half the assembly was symmetrical, I attempted to use the symmetry tool. However, this caused a large amount of parts to be created in the folder and was causing errors. To fix this, I had just added 2 instances of everything and deleted all the symmetry parts. The only few interesting parts added were the nameplate and the compression spring. To make the compression spring, it required GSD, and I had to first make a helix and then use the rip tool. The nameplate, on the other hand, required importing a DXF file. I had first written our team name in a DX file generator, and then had copied it in. Once the sketch was made, I had to scale it to fit properly and constrain it to the center.
My first assembly consists of the flywheel, the crankshaft, and the pulley. The flywheel was made using a circular pad to make the base shape, combined with patterned circular pockets to remove the material from the inside. The crankshaft consists of 2 brackets and 3 rods used to hold the pulley to the flywheel and connect to the piston. The crankshaft rotates as the engine oscillates. The pulley is used to transfer the work done by the engine to an external source, but for the purposes of this assembly, the pulley was not connected to anything. This subassembly is held together by 8 brass pins. The flywheel is made out of aluminum, the crankshaft is made out of steel, and the pulley is made out of brass. My second subassembly is the cylinder of the engine. Inside the cylinder is where the piston oscillates, which produces the work done by the engine. This subassembly consists of the top lid of the cylinder, the main body of the cylinder, the bottom lid of the cylinder, a rubber grommet through which the piston rod passes through, and 4 M4 by 8 mm screws on the top lid, and 4 M4 by 8 mm screws on the bottom lid. The cylinder top lid, body, and bottom lid are all made out of brass. This part was made using multiple circular pads for all 3 of the main parts. The top and bottom lids were simple parts only requiring a few pads and hole features to complete them. The main body of the cylinder was more complicated as it had asymmetrical geometry. The side feature, with the circle and rod sticking out of it, were made using additional pads and hole features added. The hole features seen on the circular extrusion on the right side of the cylinder extend through to the wall of the cylinder and straight up and straight down to the top and the bottom of the cylinder, stopping at the mating point of the top lid and bottom lid. On the left side, there is a circular extrusion extending out from the cylinder. My final subassembly is the piston rod and piston for the engine. The bottom of the subassembly is the piston which oscillates within the cylinder. This part is made out of bronze and has a silicone O-ring going through the middle of it. The piston rod is made of steel and extends from the piston up to the piston top. The piston top is two pieces, both made out of bronze, held together by two M5 screws. The hole going through the side of the piston top is used to attach the piston top to the crankshaft. This allows the piston's oscillation to rotate the crankshaft, which in turn rotates the flywheel and the pulley, allowing the work done by the engine to be converted to rotational energy to an external source.
All our subassemblies come together to make this final product shown in this slide. For this product, subassembly 104 was held fixed, and the rest were constrained to that. Most constraints used in this assembly were coincidence and contact. The rod was in coincidence to the center of the cylinder was in coincidence with the spindle and had a contact constraint to it. The shaft was in constraint to the bearings up top and was also finally in contact with that. By doing this, it allowed everything to spin around the axis as shown in the GIF. This last assembly was also fairly straightforward and there wasn't much difficulty. But before that, we first confirmed everything in the subassemblies were constrained properly. We did this by consistently exploring the view and updating. Doing this, we were able to see if all constraints were done properly and if anything was missed. Luckily, nothing was missed, and the rest of it was fairly simple.
This is the final rendering of the full assembly of our double oscillating steam-powered engine. There were many aspects of our project experience that went well and worked very well towards our success as a team. However, we still learned a lot about teamwork from this experience, and there are certain areas which we can improve upon for future projects, such as the final project. One of the things that we did well as a team was divide up the work evenly between the team members. Both Deepam and I had nearly an equal number of parts and assemblies to do, and we both contributed equally to the success of the project as a whole, and to the parts making up the assembly. One area that we could improve upon as a team is setting deadlines for ourselves. We did not set any deadlines as to when our work should get done, so we just kind of did it when we felt like it. This worked well for modeling the actual parts, which we finished by mid-February, but did not work well for producing the drawings of the parts, which we finished less than a week before the final project was due. This also did not work well for the report and presentation, which we are finalizing in the hours and days before the project is due in its final form. Another thing we learned during the assembly of the final product for this project was that the symmetry command within assembly design is not a very robust tool. When this tool creates symmetry of parts within the product, it also creates new files of the parts instead of creating multiple instances of the parts. This causes an unnecessary buildup of clutter, as seen in this image, nearly doubling the size of all of the files that went into this assembly. Additionally, this caused the assembly to break for certain reasons when we were trying to open it on different computers. And the main assembly file started to read part files from multiple locations, producing an all-around bad experience. We remedied this by not using the symmetry tool within assembly design and opting instead to insert the parts as multiple instances of the same part. This got rid of the extra file clutter as seen in the image and produced a more robust and efficient assembly for our product. This has been Team Jon with the double oscillating engine for EGR 305 Section 3 with Jon Yuen and Deepam Rana. Thank you and good night.